Imagine standing on a planet where the sun takes so long to cross the sky that a single day and night cycle outlasts a typical year. Here, one solar day lasts 176 Earth days. We tend to overlook the innermost orbital slot of our solar system. Wedged right up against the sun, the smallest of the 8 recognized planets is usually dismissed in favor of the atmospheric storms on Venus or the search for biology on Mars. To understand its scale, if Earth were the size of a nickel, this entire world would be roughly the size of a blueberry. Because its surface is covered in impact craters, it bears a striking resemblance to our own moon. For decades, that superficial similarity led to a persistent assumption that this was a dead, boring rock, frozen in time. But a closer look reveals a world of stark physical contradictions. This tiny cratered sphere is a highly complex, anomalous body that breaks the established rules of planetary physics. Sitting a mere 36 million miles from a parent star, you would expect a universally scorching environment. Yet, within a few hundred miles of those searing equatorial deserts, there are freezing environments that would instantly kill any unprotected biological organism. The extreme temperatures exist because the planet lacks a true atmosphere. There is no thick blanket of nitrogen or oxygen to distribute solar energy. Instead, it holds on to a tenuous exosphere, a sparse collection of atoms that fly off the surface and into space, completely incapable of trapping heat. This thermal data visualization tracks the massive temperature gradient of the planet. In the direct glare of the sun, the surface hits 430 degrees Celsius, hot enough to melt lead. But as soon as the ground rotates into the long night, that heat radiates into the vacuum of space, causing the temperature to plummet to minus 180 degrees Celsius. This staggering 600-degree thermal swing exerts tremendous physical stress on the surface minerals. Every single day and night cycle, the ground itself undergoes violent mechanical weathering through relentless thermal expansion and contraction. For a long time, scientists assumed the planet's rotation was locked in a 1-to-1 ratio with the sun, leaving one side in perpetual daylight. This orbital model shows the actual mechanics, a precise 3-to-2 spin-orbit resonance. The planet completes exactly 3 axial rotations for every 2 trips it makes around the sun. That resonance is coupled with an incredibly eccentric orbit. The distance between the planet and the sun varies wildly, from 43 million miles at its furthest point down to 29 million miles at its closest. As it approaches that closest point, called perihelion, the gravitational pull from the sun intensifies, and the planet accelerates to nearly 29 miles per second. For a short window, its orbital velocity briefly exceeds its constant rotational velocity. For an observer standing on the surface, this mathematical quirk produces a surreal illusion, apparent solar retrograde motion. The sun would appear to rise normally in the east and then perform a hesitation step. It comes to a complete halt in the sky, moves backward from west to east for several days, stops again, and then finally resumes its normal westward journey. If this reversal happens just as the sun crosses the horizon, a specific location on the planet will experience a double sunrise or a double sunset, all within an 8 Earth day window. Immense tidal forces and extreme orbital eccentricity have mathematically conspired over billions of years. The result is the solar system's only localized time reversal illusion. Look at massive impact basins like Caloris Planitia, and you see ancient frozen scars from the early solar system. But underneath that static, cratered shell, the crust is actively moving. This cross-sectional infographic compares Mercury's internal structure to our own. Earth has a standard metallic core, but Mercury is practically a planetary cannonball. Its massive iron core occupies 85% of the planet's radius, leaving only a razor-thin 250-mile outer shell. Because it is a one-plate planet with a single continuous lithosphere, something violent happens as that massive internal core cools down. The entire planet shrinks. The outer shell compresses and crumples upward, forging massive stair-step thrust faults known as lobate scarps. And the surface is changing in other ways. Deep inside impact craters, spacecraft have photographed hollows, small, bright blue, irregular depressions that lack any ancient cratering. These shallow pits prove that volatile materials like sulfur and graphite are still sublimating straight out of the crust when exposed to the vacuum. But the ultimate geographical paradox lies at the poles. Because the planet has almost zero axial tilt, the sun never rises above the rims of its deepest polar craters. Inside those permanently shadowed regions, temperatures stay near -200 degrees Celsius, preserving ancient deposits of water ice hidden under layers of dark, carbon-rich organics. The discovery of ongoing tectonic activity and evolving surface features reveals a geologically active body, one that continues to respond to the cooling of its massive iron heart. The bizarre composition we see today is a surviving physical record of the catastrophic forces that dominated the early solar nebula. New models suggest that magnetic fields in the early solar nebula acted as a gatekeeper. This Hall effect created a zone of varying viscosity that prevented material from piling up any closer than 0.3 AU to the sun, leaving Mercury as the sole survivor in the inner furnace. That local history lesson is now critical for modern astronomy. Telescopes are detecting thousands of distant rocky worlds orbiting extremely close to their parent stars. We call them exomercuries. This side-by-side data visualization compares our innermost planet with K2229b, an exoplanet located 339 light-years away. Both worlds possess incredibly high densities and massive metallic cores, orbiting their stars in tight, blistering loops. Mercury serves as the physical blueprint for extreme rocking worlds. By solving our local anomaly, we decode the physics of planets hundreds of light-years away. Despite holding the answers to planetary formation across the universe, we are only just now finishing the global map of this elusive rock. The European and Japanese space agencies launched the Bepi-Colombo mission to deploy dual orbiters designed to map the planet's complex magnetic and gravitational environment. Scheduled to achieve stable orbital insertion in 2026, the mission will utilize a laser altimeter to finally reveal the high-resolution topography of the unseen southern hemisphere. Mercury represents a fundamental fossil of the inner solar system. It is a world of profound physical and temporal contradictions, a primary record of the violent history and future of rocky worlds throughout the galaxy.